Today from MarEngBase we are going to discuss about load sharing of generators. So as learning objectives we are going to discuss what is load, and especially for generator what is load, and isochronous and Droop characteristic of governance, including AVR Droop characteristic. Then why do we need a Droop for load sharing? What is the purpose of Droop? And principle of paralleling, remote and automatic speed control of a generator from main switchboard. If you want to control the engine speed, how it's going to happen, and if the automatic power management system wants to adjust the engine RPM, the generator prime mover RPM as per the load, so how it's going to happen. So this thing we are going to discuss. Then active load sharing, reactive load sharing. Finally, I'm planning to do a simulation of taking one generator into bus bar and to show how the synchroscope is working, and then how to close the breaker and equally share the loads. So today plan is like that. Let's move to the part of load. Okay, what is the load? Here in the first diagram that we can see the phone man that he is going to lift some weight. So in that moment the load is the weight is going to lift. Here in this forklift there is a 2-ton weight which is trying to lift, but there is a huge load on this forklift, so it could not lift. For this bike, 4-person carrying, it's a heavy weight, so it is the load. The heavy weight is the load. For this man, these books, or let's say the huge weight that he carry, it is the load. Or in some cases we can consider this as a mental load. So mental stress, it's also kind of a load. So there are many kind of loads. So in physical machineries we can see load is the physical stress on a mechanical system or component as a result of the work done. It's a physical stress. So if we do not think about this physical stress, at a time the system could collapse. So now we are going to see types of loads on generator. As we know, the load on generator is the load electrical consumers which are connected to the bus bar. There are two main types of load. Active load, that means the kilowatt loads, and the reactive loads, we can see kVAR, that is reactive load. For better understanding about load and Droop characteristic, here I am going to discuss a small example. Suppose we have a system, electrical system, that we are feeding some electrical loads with the generator. So our main objective is to run this generator at a constant RPM to maintain bus bar frequency. So we don't want to run the generator at its maximum speed. We want to run the generator at a speed mostly less than its maximum speed, but it should run continuously and safely to maintain bus bar frequency. So in the same scenario, I'm going to do an example using a man. This man has to run from start to finish, not with his full speed, but he has to carry some load and he has to maintain some speed as per our requirement, and he should complete the race. So this is the requirement. Suppose without a load this man can run at his maximum speed, it's fast. But once we connect some load to his body, then he will not be able to run on that at that speed depending on his capacity, his strength, his courage, and the load that we apply. In the same scenario, the generator can run at one speed, but when we are applying loads, due to that impact of the load, the generator speed is trying to reduce, but by giving fuel we are maintaining the generator speed at constant. So here, if you want to run this man at a constant speed, as after we applying a load, then we have to feed him with energy drinks or whatever. We should supply him the energy to carry the work down. And the other important thing, if the man does not sense the load, then he will try to run its maximum speed. But even though he did not feel that he is carrying some weight, because his sensors, let's say sensors or his neuron system is not function properly, but the load is still there, so his body is under influence of that load. So eventually his body may collapse if he neglect the load, and if he not retard his performance and is trying to do the same effort as that he was doing without a load, so then his body might collapse. So to finish the race in safe manner, he has to consider and he should feel the load that he has to carry. So suppose we are going to put two person run this race, person A and B, and they both have to share a load, same like two generators trying to share a load. So this load is that much of heavy that one person will not be able to carry, and it is overweight for one person. But if they try to share the load, so then they can run with that load. So we need to carry this load from start to finish, so single person cannot do, so then we need two person. Same like in generator case, if the bus bar load is more than that a single generator can handle, then we should have two generators to handle, two or more generators to handle that load, right? Now if we ask this two persons to run, when they are equally sharing that load, so they can run safely without being overloaded. Suppose if one of this person try to run faster than the other, what is going to happen? This load will pull towards the person who's trying to run fast, and he will feel more load. So as he try to pull the weight with him, the weight will move fast. So this guy, suppose the A is trying to run fast, so then the B's rope will slack because this load is dragging as this guy trying to move fast. So then B will feel less load while A is feeling heavy load. Eventually A might collapse, because if this load, the percentage of the load that is trying to take is more than his safe working limit, so then eventually this man collapse. Same like the generator also. If the two generator has to share a load and that load is greater than the load itself can carry, so while these two generators are running in parallel, if they are not equally shared, and if the percentage of the load one generator taking is exceeding its maximum working load, that generator might eventually fail. In that case, this system I mean when the two generators are running parallel. This load should be in the center line, I mean it should be in the middle way. So then that load will not shift to here or shift towards B. So it will be in the middle path. So both generators will feel same load. So this case where the droop is involved. Suppose when this guy is trying to move fast, due to the increment of load, he feel okay, there is more load, so then he will slow down. So then the weight is trying to drag towards this person A, but as he slow down, again it will settle in the center. Same way, if the B tries to run fast, then the load is trying to pull in his direction, but as the load is coming, he will feel that more load, and then if with the load he can retard, so again the load will shift to its center. So then both generators will run safely, both personnel will run safely with the equal load sharing. So the droop is something that it's function of speed reduction with respect to 0% load to 100% load increment. Now we will discuss about this is in a graphical representation. Now we are going to discuss about governor droop behavior with this graphical representation. In this graph, x-axis is kilowatt load from 0% to 100% load. Then the y-axis is frequency or speed, frequency of the bus bar, or otherwise we can discuss as the speed of the prime mover or the generator. So as frequency is directly proportional to the frequency, here I am going to discuss with the frequency figure. Suppose our bus bar frequency is 60 Hz, and there are another two terms that here mainly we can see. One is isochronous and the other one is droop. Isochronous, it's a Greek word. Its meaning is constant speed. So in this case, it's related to governor, or let's say in a generator. The generator speed maintains constant regardless of the load. Thus the frequency remains constant. So isochronous means whether the load is 0 or whether it is 100, the frequency or the speed of the generator is constant. You can see 0% in idle also 60 Hz, at 100% also 60 Hz. So that is isochronous. So there are the governors are two types. One is isochronous, one is droop governors. So where do we need isochronous governor? Suppose your bus bar total load, full load of the bus bar is less than the capacity of your generator. So then you can use one generator in that bus bar to feed that bus, to feed that load. So in that case you can use isochronous governor, because even if you apply full load at the same time, that generator is capable to handle that load. Think like your emergency generator. The emergency generator is designed to run alone all the loads in emergency bus bar with the all loads in emergency bus bar. So it does not need any droop characteristic. Only our requirement, it has to maintain speed with the increment of the load. It does not need to feel the load increment and reduce the speed, because there will be no any load sharing. In droop governor, what is droop? Governor droop is the function of reduction in speed from 0% load to 100% load. The speed of the generator will lower as the load is getting increased. From 0% load, the governor will maintain 60 Hz. But as it's increased up to 100%, we can see the speed dropped, frequency dropped. That we call is speed droop. Speed droop is the function of reduction in speed from 0% to 100% load. Same as the governor droop, we know for sharing reactive loads, we need to have AVR. So to have equal load sharing, the AVR should have droop characteristic. Now I am going to explain in next session why this droop is important. Till now we have to have some idea what is AVR. Suppose this graph, the x-axis is load, but this time reactive load, kVAR, from 0 to 100% load change. In case of AVR, this is not the frequency or speed, it is voltage, because the AVR is handling EMF. So when there is a AVR droop in 100% load, AVR will not maintain 440, I mean the rated voltage. It will be less than the rated voltage, some percent. It's depend on the droop setting, it's 2%, 3%, depending on the system requirement. Now we are going to discuss about principle of synchronization. Suppose now one generator is running and it's feeding the bus bar. So now we can call it as running generator. And there's another generator. After checking all the physical condition of prime mover and the requirement fulfilling of mechanical side, such as loop build priming, turning gear disengage, blow through process, and after making the prime mover is standby, suppose the other generator in standby mode, that means it is started and now ready to connect to the bus bar. So now we are going to do the synchronization. When we have already running generator on the bus bar and another generator that we are going to take into load, the generator that we are going to connect, we call it incoming generator. And here we can see in these all diagrams, running and incoming. These are the generators. So there are some electrical requirements, conditions to be met prior to connecting the incoming generator to bus bar. These are the 4 requirements. The first one is phase sequence. As we know, when there's a 3-phase power supply, there will be L1, L2, L3. There are 3 phases, multiple phases. So suppose in your bus bar or in the running generator, the phase sequence is L1, L2, L3. That means this sequence is the L3 is going first, let's say, then the L2 second, and the L1 is coming thereafter. So that is the sequence. So this sequence should match with the incoming generator. Here in this example, it is not same. You can see after the red, the blue one is going, but in the running generator, after the red, the yellow is. So this should be corrected. Normally phase sequence is not affected as far as no any maintenance carried out in the generator or bus bar system, because phase sequence is normally fixed as far as the connections of the generator or the bus bar are not touched. For doing any maintenance, we can remove the connections, and while fixing back, if there's any wrong connection, then only the phase sequence might affected. So the first condition is phase sequence of both generator to be same. The second one, next thing is the voltage. Incoming generator voltage to be slightly higher than running. Here we will not say it should be same, it should be slightly higher than the running generator. Suppose this is the running generator, its voltage, and this is the incoming generator, and this incoming generator voltage should be slightly higher. When we consider the frequency also, incoming generator frequency to be slightly higher than the running generator. So this is the incoming, its frequency should be higher than the, slightly higher than the running generator. The reason for these two, voltage and frequency of incoming to be slightly higher, I will be discussed in next session. That is to maintain bus bar frequency and voltage without dip while the incoming generator is connecting to the bus bar. So the detailed explanation in next session. And the last thing is the phase angle. Both generators should be in phase. That means this is running generator and incoming generator. The phase is something like that. So we can say it is, suppose now this is running generator one phase. Let's say this is R, and incoming generator, suppose if the incoming generator R phase is not in the same phase, suppose in this time this one having plus positive and this one incoming has negative. So if this is a 440 volt system, here is minus 440, here is plus 440, then the voltage difference at this moment is 880 volts something, that voltage difference. Suppose in the same instance, if we want to close the breaker, so I can draw here. So this is the generator which we are going to connect. So this is the bus bar, this is the breaker. Now you can see here plus 440, here minus 440. The voltage difference is around almost near to 1000 volts. So while connecting this, there will be a huge current flow, and this huge current flow make a tremendous arc here, making these contacts burn, and as well as large amount of circulating current will be there due to this heavy current flow. Then there will be a heavy magnetic interaction, and this running generator and the incoming generator, one generator will be retarding, the other one trying to overspeeding. So such thing might happen, and eventually a blackout could take result. So to avoid such thing, we always prefer that running generator and running generator phase angle of the same phase, and for the incoming also should be in the same. So suppose in this point, if you are going to switch the breaker, the voltages will be both 440, so voltage different will be 0. So no any current flow will happen, even though it will be very minor current. So it is safe to close the breaker. So the fourth requirement is phase angle. Both generators should be in phase. So now we'll look into another example why we need to have slightly higher voltage and slightly higher frequency prior synchronized. To have more clear idea about this voltage and frequency requirement of this slightly higher, then this example we can discuss. Suppose man A is running while carrying a load with a speed of x. While a person running with some speed, and the same time while he running, if we add some other extra load on him, what will happen? Eventually his speed will drop. Speed will drop. So that this weight is now more load here. Now what we want to do, we want to share this load with another man. So I will choose a man who's not running, who's stationary. So now I am going to attach this load to the stationary person. What will happen? He was not running, but this guy was running. So suddenly this load will pull this guy to the same speed of this guy, pulling him to synchronism. And the same time there will be a retarding moment. This guy's speed drastically drop because this guy was stationary. He is trying to pull the other one to make him stop. This guy trying to take him back to up to his speed. So in this scenario we can see in the generator also. Suppose this is running generator. If the generator is running and if the other generator frequency is not so enough, what will happen? The bus bar frequency also get affected because this incoming generator will try to suddenly accelerate as this load will pulling that generator into synchronism. We can do much smooth load transfer by doing like this. Suppose we can keep this incoming generator at the same speed like x, same speed. Then we will connect this load. Then what will happen? Okay, as this both having the same speed, at the moment the load is connected to the B, the B's speed will be slightly dropped. So the resultant speed of this both will be little less than the x. To avoid this speed drop, or in case of generator frequency drop, or else the voltage drop, what we have to do, we can ask this guy to run at a speed x plus little high. So then as he is having more speed, at the time that we connect the load, his speed then will come down to a value that is matching with x. So then the resultant speed will not drop. So there will be a smooth load transfer. So that is why previously I was explaining the voltage and frequency should be slightly higher, because both voltage and frequency of a generator is depend on the speed of the prime mover. So in that case, to have slightly higher voltage and slightly higher frequency, we have to run the prime mover in slightly higher speed.